All right. Can you all see my screen and can you all hear me properly?
Yes, I
Yes.
can.
Yes and yes.
Fantastic. Thank you. Um, so uh, I'm just going to try to pick up some of the themes that Tom and Massimo have developed. Um, I'm going to start by sort of recapitulating some of these things. So, what I'm going to call uh, Piatelli, Palmarini, and Medeiros' lesson is that natural law, in some sense, shapes the molecule of syntax through the optimization of command relations, such that of all possible models of phrase structure, the one that's chosen is the one that minimizes probing space, disambiguating search paths for the establishment of unambiguous C-command relations. This is reminiscent of morphogenesis in the sense of Turing, and of course, the Chomskyan third factor. So what we want to explore is that formal systems that define a space of possible solutions given certain biophysical constraints. So we have two sort of levels of description, and also building on Massimo's emphasis on the pervasiveness of Fibonacci patterns, which we can think of as Turing patterns in living systems, as a consequence of general physical constraints. By physical, I don't mean material, I mean properties of physical systems. We're going to focus in this talk on a specific instantiation of natural law, since that's the name of the session. We're going to talk about the organization of information giving limited resources and the resolution of conflict, which is a point that Tom highlighted in his contribution. So we're going to talk about perception as signal analysis, right? So given a continuous signal, a successful decoder needs to recognize unit boundaries and categorize those units based on distribution, as in sort of Heresian linguistics, abstract properties such as semantic features, both, something else, whatever. So this is basically how signal analysis, the very basics of how signal analysis works. Now, if we want to provide a characterization of structure, then we also need to identify atomic units. In formal systems, in formal language theory, you would call them your terminals, and then classify atomic units in categories, such that these categories are, for example, statements over distributional properties. So they behave, they're a set of tokens that for purposes of structure-dependent processes behave similarly enough. The problems that we are concerned with are the problems of segmentation and labeling. So segmentation is a method used to identify units in a continuous signal. This may be a harder or an easier problem depending on properties of the signal. And minimally, this must rely on the identification of surface statistical regularities in the signal. So there has to be a certain amount of robustness to the signal that allows you to segment into units. And labeling takes the form of a set of symbols, labels, which can be used as variables over tokens, right? Such that if we have some structure-sensitive process, we don't have to formulate a specific rule per atomic unit. We're going to see examples, so it's not super arcane. Now, existing in the world entails solving problems of signal analysis and information compression all the time. That's because we need to organize the information that, for example, comes to our senses to create representations that we operate on. These may be linguistic or otherwise. And this is the case because we do not operate directly on the raw data from our senses. There is processing that happens before we can do things with that information. Any sampling of the environment is necessarily some kind of abstraction. We cannot sample and represent the world feature by feature. I want to mention the work by Silvia Radulescu, who has published a bunch of papers on signal analysis, in particular, what she calls rule induction. So she says rule induction is an encoding mechanism gradually driven as a natural automatic reaction by the brain sensitivity to the input complexity, which is measured in terms of entropy. So it's essentially a measure of uncertainty that's calculated in terms of conditional probabilities between items in a signal once you have identified them, interacting with the finite encoding power of the human brain, which she calls channel capacity. Of course, channel capacity is constant. The brain can do what the brain can do, but the complexity of the input can increase. And this is going to be crucial because rule induction, as she calls it, involves information compression. We need to lose some resolution in the input to free up memory and be able to operate over that information. But at the same time, we need to bear in mind, or we need to be mindful of how much information we can sort of flatten or sacrifice, lose resolution, and still have usable outputs. So this takes us to limits on sampling, because representations are always simpler than the object they represent. This is valid for humans, and that's valid for AI. That's a general principle on sampling. Necessarily involves information compression. Now, in humans, there is this interaction that has been explored a bit in the recent literature between what we can call item-based generalizations and category-based generalizations. So item-based generalizations involve operations over tokens, right? For example, statistical computation of transitional probabilities between individual items. You don't have a category yet. Now, you can transition into sort of a higher order representation, which is category-based, which involves generalization and abstraction over individual properties of tokens and the creation of variables, i.e. labels, so that you operate over labels without having to necessarily have a specific rule formulated per token. Now, I'm going to give an example. Suppose that we have some kind of continuous signal that is something like John is easy to convince. The segmentation is going to look like John is easy to convince. So far, so good, hopefully. If we assign each of these segments to a category, we get something roughly like that. We have an NP, a V, an adjective. Suppose that 2 is categorimatic, call it info, and then V. Now, there is a sense in which the grammar doesn't really care about the internal structure of XP for every X. And indeed, the argument to bring back generalized transformations in the minimalist program involves generalizing the solution that was proposed in Lectures on Government and Binding, which is, well, in 4, John can be lexically inserted at S structure. Problem was, you can have an NP that itself contains tough movement. Right. So there is a sense in which the grammar doesn't really care if it's dealing with John or it's dealing with a man who's easy to please. Those are just NPs. We can insert an NP in a designated position in a phrase structure tree. So this is an example of how you are sacrificing a certain amount of information for the greater good. A less simple example pertains to the Fibonacci or Fib grammar for friends, as presented by Massimo, which defines a cellular automaton. 0 rewrites as 1, 1 rewrites as 0, 1. So this is a simple recursive grammar that doesn't have a distinction between terminals and non-terminals. And every rule that can apply at every derivational point applies simultaneously. So generation 6 of this grammar is 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1. It's just a bunch of ones and zeros. Now, interestingly, at the string level, this grammar delivers three regularities that a few years ago I called the three laws because it's cool and dramatic. The first law is that every zero is followed by a one. That is, you're not going to find the bigram 00 in a Fibonacci string generated by this grammar. The second law is that two ones are followed by a zero. That is, you're not going to find the trigram 111. And finally, the third law, which is the non-deterministic one, tells you that a single one can be followed by either a one or a zero. So what do we do with this? Well, segmentation here is pretty trivial in the sense that you only have two expressions in your alphabet, and they are minimally, maximally distinct. You have 0 or 1. We've used blue blocks and red blocks in psycholinguistic experiments. That part is pretty simple. Now, in terms of categorization, in artificial grammar learning experiments, people acquire the first law very quickly. They realize that every 0 or every blue square is followed by a 1 or a red square. Now, notice that if every 0 is followed by a 1, you can rather quickly group 0, 1 as a constituent. And this leaves, this essentially gives you this bracketing where suddenly you have some ones that are left all alone, that are not inside any bracketing, and the distribution of the brackets recapitulates the laws. So every lonely one is followed by a bracket, and two brackets are followed by a lonely one. Right? So that's part of the self-similarity that Massimo was talking about. So we have the same kind of segmentation categorization process in natural language and in other formal systems. Now, we are doing compression. The thing is compression some kind of one-size-fits-all kind of thing? No, not really. So we're all familiar with the Chomsky hierarchy, right? In the 50s, Chomsky proposed an inclusive hierarchy of grammars and languages, such that you have unrestricted grammars that can do basically compute every computable function of the naturals. You have context-sensitive grammars if you restrict unrestricted grammars. You have context-free grammars if you restrict context-sensitive grammars, and you have regular grammars if you restrict context-free grammars. So essentially, every level in the hierarchy can characterize structures and languages that all the lower levels can, and then do more stuff. So the Chomsky hierarchy gives us a measure of complexity, right? So we can say that this grammar is more complex than this other grammar if it's higher in the hierarchy, but also we can characterize different modes of encoding information. We can talk about flat finite state or regular structures. We can talk about center embedding, context-free. We can talk about restricted crossing dependencies. It gives us a way to talk about how information is structured. Now, analogously to the Chomsky hierarchy of grammars and languages, Doug Sadie proposed a hierarchy of information compression that goes from having a perfect representation of the environment or whatever phenomenon we're interested in looking at, in which every feature in the input is represented, not really possible, to the coarsest possible representation, which is something happened. There's been some kind of change. And in between, you have a time series, which is essentially any kind of information that is tagged in time, corresponds to item-based generalizations, and category-based generalizations that includes recognizing and tracking error signals. All we need to know for the time being is that not all compression does the same thing. Right? You can compress a lot and just get something happened, or you can compress very little and get a very detailed characterization of whatever it is you're looking at. Now, crucially for my purposes, within each of these levels in the SADI hierarchy, there are different modes of encoding. There are different ways of organizing the information. Now, having different modes of encoding is what I've called mixed computation. And the idea is that there is a class of systems for which a single mode of encoding is not useful, in the sense that if we adhere to some kind of uniformity, we miss important dynamics. And therefore, our ability to make predictions about future states of the system is compromised because we're missing information about internal dynamics. This is not particularly controversial in the study of complex dynamical systems. In natural language syntax, there's people that would scoff at this. And so I present to you one of my favorite examples that I've been using it for a very long time, which is the string some fake news. Right? You can understand fake as intensive reduplication. Right? So was that fake news? Was fake news? Yes. Yes, it was. It was very fake. Or was that fake news? No, it was fake news. Right? Where the semantic value of fake is applied to the semantic value of fake news. Now, you may say you're cheating because, phonological prominence and stuff. Whatever. It has to be represented in the syntactic structure if we're going to have some kind of compositional interpretation. So like these, there are thousands of examples. Coordination works pretty much the same. Send me an email if you're interested in this particular part of thing, because this is kind of one of my babies. The contention with respect to languages is that languages vary with respect to modes of organizing information extracted from the primary linguistic data. So languages make available different modes of encoding information in addition to partaking in that information compression hierarchy, the SADI hierarchy. In physical systems, this is nothing new. So Binder and Ellis, in a very interesting paper from 2016, say, well, physical systems have been found that match the lowest three classes in the Chomsky hierarchy. Have regular languages in certain regimes of the quadratic map, context-free languages at the order chaos transition of the same logistic map, and context-sensitive languages in the chaos, in islands within islands in the standard logistic map. We're going to see what they're talking about. What I wanted to highlight here is this is not a new idea in the study of complex dynamical systems. The logistic map they're talking about is this. So this is essentially, you have a recurrence relation, right, in which each term is defined as some function of preceding terms. And 0 to 1 is a ratio existing population to maximum possible population. This was a model, among other things, of population growth that's been applied to some other things. And then R is a parameter whose value changes. So what we're diagramming here is how the system behaves as we're changing the value of our parameter R. What I want to say is that there is no single mode of encoding information that adequately captures the dynamics across all possible values of R, or at least all the values of R in the domain, in the logistic map, in the restricted domain of the logistic map that we usually consider. So for values of R between 1 and 2.3, finite state grammars are fine, as Binder and Ellis say. When you start getting period bifurcation, which are values of R between roughly 2.4 and 3.54, context tree does the job. That looks like a phrase structure tree to me. Everybody's happy. what do we do when R is approximately equal to 3.57-ish? You start getting chaotic regimes. And for that, we don't have a single mode of encoding information in the Chomsky hierarchy that gives us an adequate characterization of these dynamics. Now, because the Chomsky hierarchy is an inclusive hierarchy, you can say, why don't we go Turing complete? Why do you care about this? Just use a cannon to kill a mosquito. We're fine. Sure, but I present to you a golf green. You have an image and you have a wireframe diagram of that image. If we zoom in the wireframe diagram, notice that we have a boring Euclidean surface in that region, but when you go to the sand trap, you have kind of a saddle formation. That is an exciting hyperbolic surface. What's the point here? The point is that a successful golfer needs to correct a course, needs to consider terrain deformations in order to make accurate predictions about where the ball is going to go after applying some force to it. Right. So calculating trajectories in each of these local regions, the Euclidean and the hyperbolic, essentially forces us to shift between modes of encoding information. You need to shift from a Euclidean mode to a hyperbolic mode. And there is the relation between Euclidean and non-Euclidean geometries is not that of an inclusive hierarchy. There is no sense in which Euclidean, hyperbolic, and elliptical geometries are in any sense subsets of each other. So no single mode captures the properties of the entire space, right? The putting green and the sand trap in a way that is useful for purposes of playing golf, because we would be losing the ability to predict trajectories in one or the other local space. So a good golfer must oscillate between modes. It's also, just as an aside, unreasonable to ask a golfer to sample every single part of the grid, because if you want to have a perfect representation of that grid, the smaller your measuring stick, the bigger your representation is going to be, and that is the well-known coastline paradox, right? So how long is the coast of England? Well, that depends on your measuring stick. So what have we learned? Well, solving the segmentation categorization problem involves sampling the world, identifying units, the problems of segmentation, and labeling, right? Which entails sacrificing some information to group tokens into categories and giving up some detail. As the input becomes more complex, entropy increases, channel capacity is constant, and this is what Radulescu says, triggers a transition between low-dimensional item-based computation, which is strictly string level, very transition probability-based, and higher dimensional category-based computation, which is abstract, it depends on rule encoding and gives you hierarchical structure. Now, crucially, local and global properties of a system may not coincide, which is what I argued with mixed computation, such that systems can oscillate between different modes of representing information, each of which is valid for a local characterization of the system, but not for the entire thing. Right. So this oscillation is driven by the complexity of the input and the existence of limited resources. Now, we've looked at natural language, kind of. We've looked at certain topological spaces. We've looked at the logistic map. Are there any organizational principles that underlie the systems that we have mentioned? I'm going to contend in the second part of the talk that the answer is yes. I'm going to borrow Doug Sadie's fantastic expression, which is Turing's most important lesson. he says that his most important lesson is don't eat apples, but we have other lessons to consider too. So in the chemical basis of morphogenesis, Turing describes how complex patterns can arise from simple interactions of basic processes. So essentially, these are reaction diffusion systems. So in these systems, there's a competition between antagonistic mechanisms, which in Turing's case were chemical. So there is some kind of activator and some kind of inhibitor which diffuse across a surface, and the way in which they interact creates patterns. For example, that's the reason why tropical fish have these weird psychedelic colored patterns in their surface as opposed to just a solid color. Now, he also showed how this inherently unstable dynamics between reaction and diffusion and an activator and an inhibitor gives rise to regular forms and patterns, including Fibonacci phylotaxis. So the growth, plant growth that follows Fibonacci principles. So essentially, the lesson here is that in biological systems, the instability themselves determine the behavior of the system. The internal instabilities of the system and the interaction between those instabilities and the context in which the system has to evolve. And I suppose that the title of this slide probably reflects the mind state of many of you who are probably getting frustrated with my rambling. So what I'm going to talk about now is the concept of dynamical frustration. The concept of dynamical frustration appeared in physics in the context of the study of spin glass. So spin glass, unfortunately, is neither glass nor is it spinning. They're just lattices in which electrons are subjected to, in fancy terminology, a pairwise anti-alignment constraint. What this means is electrons can have spin up or spin down. If you have a triangular lattice and you require that no two neighboring electrons have the same spin, we can take the bottom left electron and say, well, you're a spin down. We can take the bottom right electron and say, well, you're a spin up. And that interaction is going to be pairwise anti-aligned. What do we do with the top guy? Right? A dynamical frustration, which is illustrated by this very small lattice, is a tension between mutually contradicting conditions that hold simultaneously over a dynamical system. Right? We're requiring of this lattice that it obeys contradictory conditions, and how the system behaves is determined by these this unstable dynamics. Importantly, frustration is a fundamental property of dynamical systems. Binder, in a groundbreaking work in 2008, says the essence of complexity may lie here. A system without dynamical frustration will either settle to equilibrium or grow without bounds. Now, equilibrium here is not good. If your heart entered or settled to equilibrium, you would be in trouble. If not dead, very close to it. Right? We want certain systems to be dynamically unstable, but we also don't want them to grow without bounds. In biological systems, that is cancer. So we want to keep chaos controlled. And this is what dynamical frustration will allow us to do. Now, frustration comes in three flavors across levels of organization. So you can have a geometrical frustration in which trajectories in a dynamical system are essentially at odds and point to different directions. And that's what happens with a Lorentz attractor, right? It's the cool, strange attractor that looks like a butterfly that combines stretching and folding. A scale frustration has to do with interactions across levels. So local and global tendencies can be naturally opposing. So you can have global cooperative tendencies against local rebel behavior. This has been used, for example, in sociology, unsurprisingly. So you see how in this figure, the overall dynamics of the system is characterized by counterclockwise motion, even though there is this pocket of clockwise interactions. And finally, computational frustration has to do with the fact that if you have an infinitely powerful Turing machine with an infinite memory tape, you can literally do whatever the hell you want as long as you remain within the boundaries of effective computation over naturals. But probing becomes a problem because suddenly you have an infinite space to probe. So a Turing machine may never stop a computation, or it may never even start under computational frustration. Now, we're talking about dynamical systems, and I want to emphasize the idea that these systems are studied at different levels of organization. Usually we have three scales: microscopic, mesoscopic, and macroscopic. So microscopic, the smallest one, is defined by interactions between atomic entities, particles, neurons, cells, humans, depending on what your object of study is. If you're a sociologist, your microscopic scale is going to be a human. If you are studying anatomy, then probably the cell is going to be your atomic entity. Mesoscopic level pertains to the local aggregates of interacting entities. So, for example, from the pandemic, contact bubbles were mesoscopic. If the human was your minimal irreducible unit, then contact bubbles could be seen as mesoscopic entities. If you started from a cell, you get an organ. If you started from a neuron, you can get cortical networks. And finally, macroscopic are entire systems with complex internal dynamics, for example, the weather, or societies, or the brain. Now, the tools that are used to model these levels are not the same. Usually, microscopic relations are amenable to finite state / regular / Markov formalization. Mesoscopic levels usually require systems of partial differential equations. So you want to track how a particular variable evolves as time goes by, for example. And the macroscopic level is usually way too complex. That's why instead of looking at the weather as a single system, we break down the atmosphere into regions that we can look at with somewhat more precision. Brains are frustrated. So I just chose this particular reference because I think it's really good, but there are several others. Goll and Breakspear argue that dynamical frustration is a mechanism that allows cortical functions or cortical networks to adapt to a changing environment. And you have this interaction between synchronization between interacting regions, right, which essentially has the form of coupled oscillations, and frustration, which emerges from connectivity, which emerges from local recurrent units within networks. So the same kind of arrangement appears several times throughout a network. That's called a motif. And motifs are frustrated. You have something like the pairwise anti-alignment constraint that we saw with spin glass. So you have these two things, right? Frustration at the level of motifs and synchronization at the level of interacting regions. One is a geometrical frustration, the other one is a scale frustration. Now, synchronization provides stability to the system, and frustration delivers metastability. So essentially, it delivers states that are not quite stable. They can be destabilized and the system can adapt, right? But we don't want the system to just go crazy without bounds. That's what synchronization does. Yeah, someone said something. Sorry? Someone said something. I don't know.
No. Please go ahead.
Okay. So what I want to contend is that the same stability instability tension that we just saw for brain dynamics appears as a problem in signal analysis, because the segmentation part and the categorization is based on reinforcing properties of the signal, right? So in the fib string, every 0 is followed by a 1. How do you know that? Because you keep track of instances of zeros until you can formulate that generalization. Now, the heuristics of abstraction and categorization and segmentation, well, not segmentation, but abstraction and categorization, must be flexible enough to accommodate changes in the signal. In extreme conditions, probably by extreme, I mean pathological, they may be able to allow for revisions of the internal model. But at the same time, the signal has to be robust enough to allow for generalizations. So the system cannot be so robust that it doesn't change, but it cannot be so unstable as to not be able to categorize. So this, of course, entails the existence of threshold conditions in statistical learning. Statistical regularities have to be consistent for you to generalize, but changes in the world have to be drastic enough to warrant resampling, right? And this is essentially the basis of frustration. Brain dynamics present the hallmarks of dynamical frustration. Cognition usually, but not usually, but particularly nowadays, is frequently modeled in terms of dynamical systems with fields and attractors and stuff, but also grammars and, to use Tom Bever's term, psychogrammars. There is a tension in language between production and comprehension systems, and I'm just quoting Tom here, quoting a 2008 paper, but this can be found already in 1975. Sentence processing involves complex computation of syntax with whole sentences as domains. It is vertical, and language behavior proceeds serially and incrementally. It's horizontal. From the point of view of the architecture of the grammar, it is an old observation that linear and hierarchical mechanisms impose distinct and incompatible requirements on syntax. This is already present in the dependency grammar in Tenier, right? And you can trace it all the way from the 50s, the 80s. Higginbotham and Doug Sadie, Juan Uriaguereca have made great progress with this, also Massimo and Dave. The idea is that when you have PF telling you, be low dimensional, give me something flat, and LF telling you, give me something high dimensional, a system cannot satisfy these mutually incompatible output conditions unless it oscillates between multistable states. So we have, again, the idea that we have mutually incompatible requirements imposed over a system that has to do something. You cannot just throw your hands in the air and say, right? Now, frustration is the hallmark of complex dynamical systems. Now, when we conceive of the grammar as characterizations of stable states of dynamical systems, so sort of snapshots, or if you're mathematically inclined, Poincaré maps, we can essentially take a grammatical description as a characterization of a stable state, and we can capitalize on both information compression, which is part of signal analysis, but also part of grammatical analysis. Right? Remember the example with generalized transformations. And we can take information compression and dynamical frustration as the basic organizational principles that I was asking about. Is there something that unites all these different systems? Yes, I think there is. And we have compression and frustration. Now, frustration plays a different role in grammars and in brains. So in brains, at the level of motifs, it delivers instability and therefore adaptability. In grammars, it delivers a restricted class of structures. which, spoiler alert, are the kinds of structures that Massimo was talking about. Now, in order to make sense of this, we need to understand that, or we need to sort of pay attention to the fact that understanding the limits of a system is as important as understanding the internal dynamics. So we want to know how the system works internally, but we need to know how the system breaks. What is outside of the phase space of the system? Right? The phase space for a dynamical system is a space where all possible solutions and trajectories to a dynamical system are represented. What is outside of that space is what we can characterize as ungrammaticality. Right? So if something is ill-formed, it's outside the phase space of the grammar. Again, I refer you to Tom's work. Acquisition involves both formation of statistical generalizations available to the child and the availability of structures to rationalize violations of those generalizations. So you need to be able to make sense of when the system does something it's not supposed to do, or you didn't expect it to do. Now, without constraints, the space to explore is too big. So what is my optimal solution to this dynamical frustration? If you don't have any constraints, where do you know, how do you know where to start? So in terms of acquisition, again, you have this kind of perspective. The child uses its endowment to create solutions to organize the experience in ways that interact with natural laws, emotionally driven by the innate emotional satisfaction of finding resolutions to puzzles, which is what Tom was talking about. Now, if we are looking at ways in which natural law restricts the space of available solutions, then essentially we need to pay attention to the fact that we've known since mid-50s that strings, which are pretty simple one-dimensional objects, do not uniquely specify derivations. If I give you a string, you cannot tell me which generator produced that string, like weakly generated that string, because there's potentially infinitely many that are compatible with any given string. So in this state of affairs, what hope do we have of inducing rules? Remember rule induction from Radulescu's quotation, given higher dimensional inputs, language, sensoria, whatever. Well, things become easier if the space is restricted to begin with. And Piatelli, Palmarini, and Bederes' lesson is that the space of possible grammars and syntactic molecules is bounded, is restricted, and indeed is pretty small. And furthermore, the issue becomes even more tractable if we have heuristics, if we have reliable heuristics that humans use to select between alternative modes of representation. Think, for example, about Tom's work on garden path sentences. Those heuristics make the process of picking out a solution to explore the space even more tractable. So, I proposed that there is a conspiracy at the core of language processing and structure. There is a transition between item-based and category-based generalizations. There are multiple modes of organizing information. This was essentially the first part of the talk. The second part of the talk introduced the idea that a system may be subjected to mutually incompatible requirements, so adaptability and robustness in neural networks, linearity and hierarchy in languages, anti-alignment in spin glass. Right? Now, the good news is that the space of systems that satisfy this conspiracy is actually restricted. And the physical manifestation of this conspiracy is what we call natural law. Thank you very much.